Today's third and final video, I'll discuss immiscible liquid-liquid equilibrium systems. So this is probably when we think about liquid-liquid equilibrium, what we're most familiar with. Immiscible means not mixing. So if I think about my salad dressing that's in my fridge, I have an oil phase and a water phase. I don't necessarily have any oil that is in the water phase or any water that's in the oil phase. So this is for phases that are nearly pure. So we probably should have started with this because this is the easier situation because it's, like I said, more simple because I have nearly pure compositions. So before, when I had an immiscible system, when I had a miscible system, my phase diagram kind of looked like so for the miscible. In other words, when I have a temperature and initial composition, let's say there, and I draw my tie line, I get a composition that's, say, maybe 20%, meaning that my phase 1 is 20% component 1, 80% component 2. And my other phase would be, say, 85% component 1, 15% component 2. So 15% and 20% is a significant amount of the other material that is in that phase. But for an immiscible system, my phase diagram would look more like this. So I'd be hugging the pure component, and then I'd have like a steep upper critical solution temperature. But if I pick like the same temperature and composition, now my compositions of the two phases are like 1% component 1, 99% component 2, and say 98% component 1, 2% component 2. So for immiscible systems, I have two phases that are approximately nearly pure. So how do the equations change? If I start off with my regular expressions, which are x1 alpha times gamma 1 alpha equals x1 beta gamma 2 beta, and 1 minus x1 alpha, write it neater, 1 minus x1 alpha, remember, is x2, gamma 2 alpha equals 1 minus x1 beta gamma 2 beta. And let's say that the alpha phase is rich in component 1, meaning that x1 alpha is going to 1 and x2 alpha is going to 0. And beta is the opposite, rich in component 2. How can we simplify these expressions? If we're looking at what the activity coefficients are, gamma 1 alpha is going to be for a pure phase, nearly. Right? So if x1 alpha is going to 1, that means gamma 1 alpha is going to be approximately 1. Right? Or we'll say it goes to 1. Because remember, the activity coefficient for a pure component is going to behave ideally. In other words, if my phase is almost all component 1, then the component 1 molecules that are in that phase are not even going to be aware of the presence of any of the component 2 molecules. I made a mistake there. This should be phi 1 beta. Right? Because this is nearly pure. On the flip side, gamma 1 beta is going to be equal to the infinite dilution activity coefficient. So we denote that with y1 or gamma 1 infinity. Right, so the infinite dilution activity coefficient. Similarly, for the beta phase, I'll have gamma 1 beta is going to be approximately equal to gamma 1 infinity. Wait a minute, no. Gamma 2 beta. Sorry, I misspoke again. Gamma 2 alpha. Gamma 2 alpha is equal to the infinite dilution activity coefficient for component 2. While gamma 2 beta, because beta is rich in component 2, is going to be equal to 1, or nearly 1. So when I make these simplifications, I'm going to get x1 alpha and gamma 1 alpha, remember, was 1, equals x1 beta times gamma 1 infinity and 1 minus x1 alpha, gamma 2 infinity equals 1 minus x1 beta, and times 1. All right, so when we have a dilute system, we can measure or estimate what the infinite dilution activity coefficients are. So again, these are much simpler equations to solve. So just as an example, let's say we have the following, and I'll pause to write out the problem statement. So take, for example, at 307 degrees Kelvin, a system of water and diethyl ether is in liquid-liquid equilibrium. One phase contains 98.89% water. The other phase contains 4.95% water. What are the infinite dilution activity coefficients for this temperature? So we could just plug in numbers to our equations. So if I take just the equations that I wrote above, and I'll just write it up here. X1 alpha, so we just designate phase 1 will be the water-rich phase, and we'll call water our component 1. So X1 alpha is 0.9889 is equal to X1 beta, so 0.0495 times gamma 1 infinity. And this is as simple as just dividing through. So we can perform this division and say gamma 1 infinity is 19.98, and the other one, which is, let's see, 1 minus 0.9889 is 0.0111. Right, did I do that right? I hope I did that right. Let's see, I think so. Yep, times gamma 2 infinity equals 1 minus, this is 0.9505. Did I do that one right? I don't think I did that one right. Yeah, I did do it right. 9505 times 1. Another simple division gives me gamma 2 infinity is equal to 85.63. Now notice that my other activity coefficients are 1. So my gamma 1 is ranging from 1 to almost 20. And my gamma 2 is ranging from 1 to almost 85. So the takeaway here is for an immiscible system, my gamma infinities, my infinite dilution activity coefficients are large. Infinite dilution activity coefficients are greater than 10. Are usually much greater than 10. And this is indicative of a system that is highly non-ideal, which is what we would expect. So for a system that is totally immiscible, that means there's no intermixing at all. That means that the system is just that much more non-ideal behaving. All right, so that'll wrap up this short third video. Next time we'll talk about vapor-liquid equilibrium, which will be another fun topic. So you can have 3 phases that coexist all together in phase equilibrium. See you next time.